All right, here's a quiz I gave today in class, and this one is over principal stresses. So what we've got is this bracket. It's bolted on here on this wall, and then we've got this applied force right here, 6 kilonewtons. And we can see the cross-sectional area right here. What we want to do is find the principal stresses acting at point B, which is right here. And basically it says it's on the web here just below that horizontal segment. And we want to show the results on a properly oriented element located to this point. And then to shorten the quiz, because we didn't have a lot of time in class, I gave the centroid location and then the moment of inertia value. So that way they didn't have to calculate it. So I went ahead and drew this little picture out of the cross-sectional area. So this is the centroid location right here at C. So you can see that's measured up from the bottom. And then here's point B right here at the very top of the web. So for principal stresses, when we want to find that means I need to know the normal stress at B and I need to know the shear stress at B. In order to find those things, we need to know the internal loadings. So I'm going to have to section this right here. And then I have two choices. I can use this side or this side. Well, I'm going to pick this side because if I use this left side, I have to deal with this fixed support, and I don't want to deal with that. So I'm going to use the right side to find my internal loadings. So let's go ahead and draw that out and label everything on there. All right, so we're sectioning it here, and y'all know my drawing is not going to be the best. There we go. It's as good as it's going to get. Now let's put the 6 kilonewton force on here. And it's at that 3, 4, 5 triangle. So that's 3, 4, and then 5. And then we have to put our internal loadings. All right, so I've sectioned it right here. So right here we'll have our internal loadings. Let's go ahead and put N, V, and M. So the normal force, and I'm going to say that it's going out. Now, that's not going out. So I don't know if that's correct or not, right? But that's the way I'm going to put it. And then we're going to have V. So let's find V. Whoops. So V, let's put that going up. And then we're going to have our bending moment M. Okay. So I've got that. Now let's put our distances on here, because I'm going to take the moment about this point here. And let's label this point over here. Let's make it green, I guess. Right here is going to be C. So that's where we cut it. And basically we want to take our moment at that centroid of that cross-sectional area. So if we put our distances then, this horizontal distance from here over to here, that is going to be the 800. And that's millimeters, so I'm going to put it in meters, so it's going to be 0.08 meters. And then the vertical distance, I need to go from here up to C, which remember C is the centroid there of the cross-sectional area. So that means I'm going to have this 300 plus the distance to get to the centroid. So that's going to be this distance here. Because notice this is measured from the bottom of the cross-sectional area, which coincides with this point A here. So that's the value we'll use for this distance. All right, so we're going up to here. And then when you add the 300 plus that centroid distance, y'all, it keeps going to the eraser. We're going to get 0.3991 meters. Now we can go through and do our internal loadings. So let's use our equilibrium equations for that. Let's do the x direction first. To the right will be positive. So I have a negative N. And then over here, I've got this component. All right, so that's going to be negative. And then we're going to do 6 times 3/5. So we have that, set it to 0. So then move it over, it's going to be a negative, and it's 18 over 5. And let's see what that value is. So that'll be negative 3.6, and that'll be kilonewtons. Let's go to the y direction. Up's positive. So for y, I've got this v, and then I've got this component here. So this one will be 6 times 4/5, and it'll be negative. So we're going to have, you guys, I did it again. So we're going to have v minus 6 times 4/5. Set that to 0, solve for v. That is a positive 4.8 kilonewtons. And then lastly, let's find the bending moment. So counterclockwise is positive. Now we know we're going to have this. I just assumed it was counterclockwise, which would be positive. And then we have to go through and calculate the moments due to these components here. All right, so let's do this horizontal component first. So we'll have that. The distance is going to be this vertical distance, the 0.3991. And since it's going this way, it's going to be a clockwise rotation, right? So we're going to have our m minus 6 times 3/5. That's that x component. And then the distance is 0.3991. Lastly, we've got this component here. This is also a clockwise rotation, so it'll be negative. And the force will be 6 times 4/5. And then the distance, since I've got a vertical force, I need this horizontal distance, so 0.8. Right, so we got negative 6 times 4/5 times 0.8, set that to 0, and then we can find m. That will be a positive 5.276. All right, so we got that. Whoops. So now we can do kilonewton meters there. Okay, so we've got the internal loadings there, and now what should we do? Well, now I have to go through and find my normal stress. Let's do normal stress first, and then we'll do shear stress. So looking at these internal loadings, we got these three things. Which ones of those are going to cause normal stress? Well, the normal force obviously would be a good choice. And then we've got the moment, right? The bending moment causes that bending stress, which is a tensile or compressive type of normal stress, right? So we're going to use both of these. So that means our normal force, which is sigma, is going to be equal to our normal force over the area plus my over I. So I'm just writing a generic equation here, but that'll be it. So the N over A takes into account the stress caused by the normal force, and then the my over I, that counts the bending stress. All right, so we're going to plug in our values and then see if those should be positive or negative. All right, so N is going to be 3.6, and it's kilonewtons, and we'll do the sign in just a second. And now I need the area, so I need the cross-sectional area. I don't have that calculated. We need to find it. So if we look up here, we've got two rectangles. We've got this top one. So if we do it in meters, we'll have 0.15 times 0.012. So we have that. And then we're going to add to it this vertical rectangle, which is going to be 0.13 times 0.015. And let's see what that gives us. Okay, so I wrote the value down, 0.00375 square meters. So that's what we'll put over here. And now let's see, is it tensile or compressive? Well, let's look at our drawing here. I drew it going out, and it's negative, so that means really it's going in. So if it's pushing in, and B is like right here, that's going to be a compressive stress on B, right? Because it's pushing in to B. So that means this needs to be negative. All right. So we've got that, and then the bending stress here, let's put the values, then we'll look at the sign. So the moment is 5.276, it's kilonewton meters, and now I need the Y. Well, what is the Y going to be? Well, remember, the y is the distance from the neutral axis to the point of interest, right? And the neutral axis goes through the centroid, right? So that means this right here is the neutral axis. So we have our neutral axis, and I need to get to point B. So basically I need this distance right here, right? That's what we're looking for. So how can we find that? Well, if we look, the total length, if we look up here, this has to be 130, right? So that means from here to here is 130, and I know this distance is the 0.0991. So to get this, I would just subtract those values, right? So we're going to multiply by 0.13 minus 0.0991. Oh, we got a different color here. And then let's put that over I. So moment of inertia, I gave that in the problem. What was that? So here it is right here. So we just need to write that value down here. All right, so that's going to be 7.4862 times 10 to the negative 6. And that's meters to the fourth. All right, now let's look at the sign. So should it be positive or negative? Remember, it's positive if it's tensile at the point B. It's going to be negative if it's compressive at B. So if we look at my diagram, I said it was going counterclockwise. We got a positive number, so that, ensures that this is indeed counterclockwise. So when we do our right-hand rule, remember B is right here, my hand's going to go in this direction. So I'm pulling away from B, which means it's tensile. So since it's tensile, we're going to have a positive number. So this we will add right there. And then let's go ahead and calculate that value. And what we get is 2,000, well, actually not 2, it's 20,817.2. And then that would be Pascal. Actually, it's not Pascal, it's kilopascal. All right, so now we've got that in kilopascal. And if you wanted, you could put it in megapascal. Let's go ahead and do that so we don't have this huge number. So just divide by 1,000. So that'll be 20.817 megapascal. All right, and it's positive, so overall we have a tensile stress at B. So that takes care of the normal stress. Now let's do the shear stress. All right, so the equation that we'll use will just be that shear formula, so VQ over IT. And we know what V is, right? That was right here, 4.8. That was our shear at that cross-sectional area where we sectioned it. I, we already know. We need to find Q. So for Q, we're going to look here at this cross-sectional area. Now, I'm looking for the shear at this point B, right? So for Q, remember we have to do the calculation. Let me write it out here. Y bar prime, A prime. All right, that's the notation from the Hibbeler book that I teach out of. So Y bar prime is basically going to be the distance from the neutral axis to the centroid of the region that we need to analyze for Q. So in this case, since B is right here, I'm going to use this piece right here. All right. So this is going to be my A prime. So let's make that pink there. So this is A prime. So if that's A prime, I need to go to here. So this is the centroid for A prime. So this is the value I need for Y bar prime. Okay, because we got to get to the centroid of that, but it's got to be measured from the neutral axis. All right, and if this is unfamiliar to you, it is in a transverse shear section in whatever textbook you're using. So in the Hibbeler book, that would be in chapter 7. All right, but I'm assuming everybody remembers that stuff. So now let's find that. So y bar prime is this distance here. All right, so this is going to be, you know, halfway from the top, and this total length is 0.012, so that means we're going to have 0.006 here, and basically we need to find that difference. So let's look at the values we got. So if we look, the total vertical distance here is 130 plus 12, so that's 142. So we're going to have 142. Let's write these down. And we want to put them in meters, so 0.142. We got that total length. And then I want to subtract the 0.012 over 2. And that gets rid of this distance here. And then I need to get rid of this distance here. So we'll subtract 0.0991. These are all meters. All right, and then we need to find the area of this pink shaded region. So this top rectangle here, essentially. So we'll just have 0.15 times 0.012. And those are all in meters also. Okay, so Q, let's calculate that. That gives us 0.000066. All right, and then that's meters cubed. Okay, so we've got that, and T, we can find that in just a second. So let's go ahead and start writing out our values. So our shear stress at B is going to be the shear force, which is 4.8 kilonewtons. I need Q, which is this tiny little number here that we just found. And then we need to put that over I. So I is this 7.4862 times 10 to the negative 6 number. And then T. All right, now remember T, the easiest way to find that is where your neutral axis is. You want to see how much material your neutral axis is in contact with. That'll be the length for T. So if I look in this case, we've got this length right here. Right, so just the width of the web, basically. And what is that length? We look up here, it's 15. All right, so 15 millimeters or 0.015 meters. So let's do that. Whoops. Okay. So now we've got that, and let me put it in the calculator. And that gives us 2,821.19, and that again is kilopascal. So if we want that in megapascal, just divide by 1,000, and that'll be 2.82 megapascal. So now we've got that. Okay, now let's draw these values on an element. So here is our element at B, and then we need to label these stresses on here. So first of all, we've got our normal stress. All right, this was our normal stress. It's a positive, so it's tensile. So that'll be the stress in this like X direction here. Actually, let me make it a different color. So we've got one here, and then opposite side. So that is going to be 20.817 megapascal. And then I got to do the shear stress. All right, so the shear stress, the way I like to do it, I'm not sure if I'm the only one that does it this way, but I go to my free body diagram and I take a little element and I slide it in right where I did the cut, like right here. And then I see which way the shear is going on the face at the cut. So here I've got the face at the cut. Shear is going up this way. I had a positive, so it is, oh my goodness. So it is going up, right? So that means over here on this element, I can put this one here, right? Because this matches that face that was at the cut section. And then complementary property of shear, that means we have to have one going down here, and then we're going to have one here and one here. And this value would be 2.82 megapascal. Okay, so we're getting close to being done. These problems are really long. All right, so now we've got that. Now remember, we are in the standard XY frame here. Now I need to use my principal stress equations. So let's write down what that is. I'll write it down here and then come back in just a second. All right, so I went ahead and I wrote down our equation for principal stress. So this is the standard equation that you can use. You could also do Moore's circle. I just haven't covered Moore's circle yet in class. We're going to start that on Wednesday. So now with this equation, I need to find, y'all, it keeps going to the eraser. Okay. I need to find sigma x, sigma y, and then this tau xy. Those are going to come from this element. All right, so remember, this is the x direction, this is the y direction. So with that, I know that sigma x is going to be a positive 20.817 megapascal. All right, it's positive because it's going away from the element, it's tensile, going in that positive x direction. Sigma y, well, I don't have anything in the y direction here, right? So that's got to be 0. So sigma y will be 0. And then tau xy, well, we've got 2.82, but is that positive or negative? The easiest way to figure out the sign is we look in this quadrant right here, right? Because we got x and then y. So we want to look in this quadrant, and if the arrows come together and make that plus sign, it's a positive. So we don't have that here because ours are going away from each other, right? So that means it's a negative. So we're going to have a negative 2.82 megapascal. And now we just have to plug them into this equation here for principal stress. All right, so sigma 1 and 2, let's put those in here. We're going to have 20.817. Sigma y is 0, so that doesn't do anything. Put that over 2 plus minus square root of 20.817 minus 0 over 2, square that, plus the negative 2.82 squared. And then we go through and calculate both of those values. All right, I went through and calculated those. So you can see the values for this first term here, we get 10.41, and then for the square root term, we get 10.78. I need to add these two, and then I need to subtract, and that gives me these two values. Now, sigma 1, that's always going to be the bigger value, so that's going to be the 21.19. So that'll be 21.19, that's megapascal. And then sigma 2 is going to be negative 0.37 megapascal. All right. And then those are the principal stresses. That's really all it asked for. If we want to know the orientation, so we can draw it on an element, which actually we need to do that. What we need to do is use our tangent to theta p equation. And remember, that is going to be equal to what? Well, it's going to be equal to your shear stress over, let's see, what is that? Sigma x minus sigma y over 2. So with our values, we're going to have a negative 2.82. We put that over our sigma x, which was 20.817, minus 0, because we don't have a sigma y, divide by 2. So now let me put that in the calculator, and then we'll see what we get. What we get, though, is going to be 2 theta p. So let's do the arc tangent, see what we get. So what we get here is that 2 theta p is the arc tangent of negative 0.2709. So that means 2 theta p is going to be negative 15.16 degrees. And if I want just theta p, we just divide by 2. And what is that? Let's see, negative 7.58 degrees. All right, so that is going to be theta p. So now we got that angle. So let's see which stress that goes with, because right now I don't really know. So let's go ahead. We're going to plug that angle into our sigma x prime equation. So remember that finds the normal stress when you've rotated through that orientation angle. So that equation, let's write that down, is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta. So we're going to plug that angle in with all of our stress values and see which sigma that goes with. So let's see. Let's mark out these y's first. This is 0, this is 0. So it'll simplify it a little bit. So that's going to give us 20.817 over 2 plus 20.817 over 2 cosine 2 theta. So we already know 2 theta right here is negative 15.16. And then we got our shear stress, which is negative 2.82, sine 2 theta, which would be negative 15.16. So let's calculate that and see what we get for the stress. So if you plug all that into a calculator, you're going to get 21.19, and that would be megapascal. So if we look, this value is the same as this value. So that means this theta p is theta p1. Okay, so theta p1 is negative 7.58. So now we can use that to draw our element that's oriented correctly to get these principal stresses. And I'm out of room, so let's do that over here. So here's our element, and we've rotated it. Positive rotation would be counterclockwise, so this is a negative angle, right? It's negative 0.758, so we have to go clockwise. So if that's clockwise, that means our x prime is right here, y prime would be here. So now we've got that. And let's go ahead and draw our stresses here. So let's see, we got this one, and that is our sigma 1. So 21.19 megapascal goes there and there. And then the sigma 2 will be on the other faces. Now that one's negative, right? So we're going to have negative going down, then up into there. So that'll be 0.37 megapascal. And then we can put this angle here is 7.58 degrees. Okay, so that was a long problem, but hopefully you can see how to go through, calculate your normal stress, your shear stress, put it all together to get your principal stresses as well as your orientation angle. So basically this means that point B, if we were to rotate that plane there through an angle of 7.58 going clockwise, we'd get these maximum stresses. All right, so if you were designing something, you'd want to make sure your object can withstand these stresses here, all right, because those would be your max stress values. Okay, hopefully you like that one. I'll see y'all again next time for another one.